Okay, I think we're all set to start. Today we're going to be looking at section 3.5, exponential and logarithmic models. All right. Here are the 5 most common mathematical models involving exponential and logarithmic functions. We're very familiar with exponential growth and exponential decay. All right. If we have something like exponential growth, oftentimes to be exponential growth, if E is our base, then our B, our exponent, has to be positive to make sure that our base is still greater than 1. So essentially what that's going to look like, we know that exponential growth with natural base E is going to be increasing from left to right, and this would have the ordered pair 0a. All right, so that's a very common function that's used to model lots of different things. Similarly, if we have the natural base and we want it to be exponential decay, then that means that our exponent has to be negative. So I've said B is greater than 0, and then notice that this is negative. So that indicates that that does have to be a negative exponent that you see as the exponent with that natural base E. And then again, we have that starting point at 0a. There's also another model that can be used is the Gaussian model. And for the rest of these, the only thing, like for the Gaussian and logistic growth, it's just the idea of being able to recognize what the equation is and then what the graph would look like. So in the Gaussian model, we have A times E, and then the exponent is actually the opposite of the quantity x minus b squared, over c. And the graph in this case looks like a bell curve, okay? And again, the y-intercept is at 0a. But the Gaussian model has A times E to a bunch of stuff, essentially, and it looks like a bell curve. The logistics growth function is another one that is really popular. What happens is that in the logistics growth function, there's like an asymptote, usually at y equals 0. And then there's another asymptote up here. And this asymptote is at y equals a. And what happens in the logistics growth function is that it kind of looks like that. It's almost like a cube root function, but cube root functions, keep going. And here the logistics growth is bound by these values. This often represents like populations, because they'll like increase real quickly and then like the growth rate starts to kind of taper off a little bit. So I've seen that a lot with population using logistics growth. And of course, we know the logarithmic model is that we can have a plus b times the natural log of x, or a plus b times the common log of x. And we know in those problems that there is a vertical asymptote somewhere, and the domain is bound by that vertical asymptote, and then the range would be all real numbers, okay? So just make sure, again, that you are able to identify the model if you were given a picture or the equation, so either one, just make sure you could match. That's it, okay? But let's look at modeling in general. And here's one that we've looked at before, the idea of interest. Says the interest in a savings account is compounded continuously. R is 8%, and the amount in the account after 10 years is $20,000. Find the initial investment and the time to double. Well, first of all, when it's compounded continuously, that tells us that we're going to use that equation, A equals P times E to the RT. Okay, so we just need to know what to put into those different pieces. So we look here, we know that R is 8%, so our R is 0.08. It's after 10 years, that tells us that T is 10. And then it tells us that the initial, that we want the amount to be $20,000. So this is telling me not the initial amount, but this is telling me that they want the amount to be $20,000. So we're actually looking for P. We're looking for the initial investment P in this problem. Well, let's put everything in. And for A, we can put 20,000. We don't know P. And then we have E to the 0.08 times 10. Okay. And so if we isolate P, we can see that we would have 20,000 over E to the 0.8. So I just multiplied the 0.08 times 10. And then you would just put that in your calculator. So in this case, you could put 20,000, and then you can just divide it by, and then remember to get to E on this type of calculator, you have to go into the log part. If you're using your graphing calculator on assignments, we know that the e to the x key is here, the second function of the natural log key. But here we get that we have $8,986.58. So if we round to the nearest penny, which would make sense in this case, we would get that is our initial investment, $8,986.58. So then to do the next part is asking for the time to double. And you could put this in, but that's kind of a hot mess, isn't it? The time to double is asking you basically what is going to happen when the principal is doubled. So when it says time to double, you can just put in 2p in place of a. So again, regardless of the start amount, regardless of if you started with $8,900 or $7,000 or whatever, it doesn't matter. It would take the same time to double regardless of the start amount. And so here, what we can do is use this a equals p times e to the rt. And this time in for a, we're going to put 2p equals, we don't care what the principal was, all right, times e, and then we have the r is 0.08, and then t we don't know, sorry. We're looking for t, the time. Okay, so notice you could then divide both sides by p, and we get 2 equals e to the 0.08 t. And now we want to solve this equation. Well, how would we solve that equation? Well, we could rewrite it in logarithmic form. So you could think about it as taking the natural log of both sides, or you could rewrite it in logarithmic form. This would be the same as the natural log of 2 equals 0.08 t, based on what we did the other day. So that means that t is going to be the natural log of 2 over 0.08. So not the natural log of 2 over 0.08, but the natural log of 2 divided by 0.08. And so we can put that in here. We have the natural log of 2. Oops. The natural log, oh wow. And then close parentheses and divide that by 0.08. And I see about 8.66 years, okay? So notice that we get about 8.664-ish years, okay? But remember that we want it to double. If we cut off after 8.664 years, if we cut off after 8.664 years, we wouldn't quite make it, would we? Like there's more of it to go. So if someone's going to be super nitpicky, they might say, you know what, if I need the time to double, the 8.664 years isn't going to cut it. So maybe to make sure that it gets there, that it does double, that it's not like just short of doubling, then I'm going to say it's going to take 8.665 years to double. Okay, so here my justification would be, but not quite. Okay. Okay, so that's example 1. All right, in example 2, we have the population of a city is P equals 1,350 e to the kt, where t equals 0 represents the year 2000. So it says in 1984, the population was 1775. Let's find the value of k and use this value to estimate the population in the year 2110. All right, so we use this, and the first thing is maybe to decide what this 1984 is telling us. Well, if t equals 0 represents the year 2000, 1984 is 16 years before that, so that would mean that t is -16 in that case. It does say that at that point, the population was 1,175. So at that point, we can say that P was 1,175. And we can use that to find the value of K. So let's put that in here. So in place of P, we have 1,175. And then we have 1350 e to the K times -16, okay? So again, we put these values in because when t is -16, the population was 1,175. Well, I'm going to try to isolate k, so try to solve for k. So I could start by dividing by 1350. And again, let's not write any decimals because that chops off our work. So then what I would do, again, k is part of the exponent. So I would either take the natural log of both sides or rewrite in logarithmic form. So we would have log base e of 1,175 over 1,350 is going to be -16k. So what that means is that k is going to be the natural log of 1,175 over 1,350 divided by -16. So that's my value for k. So let's find what that is in the calculator. All right, so again, we haven't written any decimals yet. So I'm going to take then the natural log of 1,175 over 1,350. And then divide that, you can still see it, divide that by -16, okay? And I get this super small answer. Here's what I want you to do. I don't want you to write, I mean, you can write that decimal down. I want you to use that exact answer. How do you do that? This thing called the store key. On these type of calculators, notice that down here, there's the store, and then there's this X piece here. I would like you to store that as X. And notice that here it says answer is going to go in for X, and then you press enter. And what that means is that anytime you press X, it's going to be recognized as that number, okay? If you were to do this on the graphing calculator, let me put that in here real quick. All right, so again, on the graphing calculator, I got this value. What you would do here is, again, you would go down to the store key that's next to the number 1 and said I would hit store and then the X key, press enter, and then it's in the graphing calculator as well. So that means that now if you press the X key on the home screen, it's going to give that to you. So that's the way I'd like you to do that. So, I mean, we can write down what this is. I think I did that in my notes, that that's going to be about 0.008677278, whatever, okay? But what we're going to do is we're going to store this in the calculator so that our answer is as specific as possible, okay? Again, this is not a negative. It's a, I don't know, it's a bird. Okay, so now we're going to use this value to estimate the population in the year 2110. So we knew that our equation was P equals 1350 E times K times T. And in 2110, notice that this is telling us that our T value would be 110 years. Okay, but this K value is going to be from the calculator. So then the way you would put that in is you would just say, you would just type that in. So you would have 1,350, and then you would have times E, and then you would raise it to the 110. And then remember how we had that stored as X? You just type it into the calculator, right? Just like that. Or you could put X times 110, I don't care, okay? And then you press enter, and then it gives you that answer. And so that's so much nicer and accurate because we're not chopping off any decimal places. So for our P, we got about 3,506.454, okay, ish. But this is talking about people, all right? And so if we're looking at the population, we would say that the population would be about 3,506 people, right? In example 3, radioactive decay, all right, that can be modeled with an exponential decay model. Again, so we have C, the amount that's left, is equal to C sub 0, the start amount, times E to the KT. So suppose that the half-life of a radioactive decay substance is 1,620 years. What this means is that when you see something like half-life, that means that it doesn't even matter what you start with, that what you end up with is half of what you start with. So again, if you talk about the half-life, you're going to have that C equals 1/2 of the C sub 0, regardless of where we start. We don't even care. But half-life means that you're going to let C be half of your starting amount. And this is saying that the time is going to be 16 years, or sorry, is 1,620 years. So that's telling us that there is a half-life. And it says if there is initially 10 grams of the substance, how much is left after 1,000 years? Well, we're not even going to deal with that part yet. This is what we're going to use first, okay? We're going to use this part of the sentence first. So let's put that in. In place of C, that's going to be like 1/2 of whatever our start amount was. And then that's going to equal C sub 0 times E, and then to the K times T. So K times 1620 would be like 1620K. Again, we can see that we would just divide both sides by C sub 0 to get 1/2 equals E to the 1620K. Now we would use the way we solve logarithmic equations, again, either taking the natural log of each side or rewriting in logarithmic form to get that the natural log of 1/2 is equal to 1,620K. And we can see then that K would be the natural log of 1/2 over 1,620. We can again put that in our calculator and we can store that as our value, okay? So again, we don't use this initial amount at first. We don't have to, all right? We can just use this piece to help us find what K is. I mean, I guess you could use it, but okay. So you're gonna take the natural log of 1/2, oops, and then we're going to divide that by the 1620. Now this is my new K value. So all you have to do is just press store X and press enter again. And again, now every time you press X, it's going to give us that new value that you stored there. All right. So if you'd like to write it down, it does end up being negative 0.000427869 again, but you're just going to store this in the calculator. Okay. And we do that so that the next part of our problem is going to be accurate. Now they're telling you that there is 10 grams of the substance. So now we can see how much is going to be left after 1,000 years. So now what we're going to do is say, all right, if there's initially 10 grams, now let's say that C sub 0 is 10. And let's see that T is 1,000. What would we end up with? So here we would have C equals, our initial amount we said was 10. And then we have times E to the K times 1,000. So we could write that as 1,000 K. And again, that K value is going to be whatever we had from the calculator. Okay, so here's my calculator. So I would type that in. So I would take 10 and then times E to the 1,000. And then X represents the K value that I found. And then I can see that there's going to be about 6.519 grams left. All right. So those are the two parts of the problems. Notice that we find what K is, and then we can use it with like the new amount of time that they're giving us. So this is going to be very similar. It says the half-life of carbon is 5,730 years. What percent of the original amount of carbon-14 remains in a fossil after 1,000 years? Okay. Well, first we have to figure out how much is going to be left. So what we would do, so the percent left, I guess we'll talk about that. So the percent that would be remaining in this problem would be the new amount over the original amount. So C over C sub 0 would be the percent that's left. Okay, because C is how much carbon is in there now. C sub 0 is where we started. So the now amount over the original amount then would be the percentage that's left. Okay. So to help us do that, let's just put in what we know. Again, here we have the half-life of carbon. So if we're looking at the half-life of carbon, that means that we're taking half of whatever's left. Again, we don't know whatever's left, right? But we can just use that, or what we started with, but we can use the C sub 0. And then we're going to multiply that times E. And then again to the 5,730 K. So I know that our function has E to the KT, but in this case we know T, so a lot of times we'll just put that as the little coefficient of K. Again, dividing by C sub 0, we could get 1/2 equals 5,730 K. Rewriting in logarithmic form, we would get the natural log of 1/2 is 5,730 K. And that K is the natural log of 1/2 over 5,730. So once again, I would just go to my calculator and type in what is the natural log of 1/2 divided by 5,730. And this is my K value, okay? So again, I'm not even going to write it this time. I'm just going to store it in the calculator. All right. And so the percentage left would be C over C times 0. So let's think about what that would be. If you think about the equation, C equals C times 0 e to the KT. All right. Notice if I divide by C sub 0, that gives me E to the KT. So that means that the percentage left is really just going to be E to the kt. That's another way for me to express that. And so this wants to know what's left after 1,000 years. So after 1,000 years, that means that we would have put our k value in from the calculator again. So I know it looks like a variable, but it's really a constant that's from the calculator. And then we wanted to know how much was left after 1,000 years. So we put that 1,000 in. So that would be our percentage that's left. So then we would just say, all right, oh, I have to store this for X. Let's do that. That would be a good plan. Okay, so now that's going to be my storage for X in the calculator. So now, again, I'm taking e to the 1,000 times our new X. And that gives me about 0.886, which means that 88.6% is left after 1,000 years. Okay. And so that's a way that we could attack something like that, right? So again, a lot of this is just finding your K and then going from there. Example 5, this one's a little different. This says, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. Find an exponential model. So we're going to use this. F of x equals a times e to the bx for the fly population f of x, where x is the time in days. And then we'll find out how many flies there will be after 5 days. So what this problem tells us is two things. It gives us two different scenarios, all right? Two different times. After 2 days, there were 100 flies, which means that 2 100 is an ordered pair that would make this work. And also it says after 4 days, there were 300 flies. So we would have 4 300 as another ordered pair. And they gave us this function, f of x equals a times e to the bx. And we aren't sure what A is, we're not sure what B is, but if we have these 2 points, when we have these 2 points, then we can figure out what that is. So let's make a system of equations of sorts. So if I use 100, or it's 2 comma 100 in this equation, I would end up with 100 equals A times e to the 2b. And if I use 300 in this equation, that's going to be 300 equals a times e to the 4b. So again, I just substituted the y for f of x and the x in for the x. And we know in a system of equations, we want to isolate one of the variables. So e, remember, is not a variable, it's a constant. So I would isolate either a or b. I pick a, all right, because that's going to be easier to isolate. But which equation should you choose? I always choose the one that has the smaller exponent. So I'm going to isolate a here. And I'm going to find that a is 100 over e to the 2b. And then what I'm going to do is I'm going to put that into this equation. So then into that equation, I'm going to say, all right, so 300 equals, in place of a, I can put 100 over e to the 2b times e to the 4b. Okay, so again, all I did is I took this equation and replaced the a with the a value that we found from this guy over here on the left. Well, the reason that I like doing the smaller one is because you can see, you can use the properties of exponents to simplify this. We can keep the base, subtract the exponents. So it means that 300 equals 100 times, 300 equals 100 times e to the 2b. Then we can divide by 100. And then we can take the natural log or rewrite it in log form. and I find that b is the natural log of 3 over 2. Okay, again, just so that we're accurate, let's store this value. Okay, and this value ends up being, let's write down what this value is. If we take the natural log of 3 and then over 2, then that gives me about 0.549-ish. Okay, but let's make sure that I use that stored value going forward. What are we using that stored value for? Well, let's now find what A is. So now what we'll do is we'll put that B value that we found in the calculator. Okay, so now we can type in 100 over e to the 2x, that's from our calculator, and then we can find what that is. So let's take 100 divided by e to the 2x. And look, we have 33.3 repeating. And so I know that 0.3 repeating is like 1/3. So A is 33 1/3. I usually like improper fractions. I know that's why I can't teach like middle school. So I would say that E is 100/3, or you could write 33 1/3. I guess it's fine. But you're going to use those pieces to write your equation. Notice that you have your A and you have your B value. So your model would be f of x equals 100/3, or 33 1/3, times e to the 0.549x. Okay, so here I'd let you round. I might even make this approximately equal to because of that. All right, so this is our model for the fly population. So we did that by using the 2 given points and creating a system of equations. So then the last thing they want to know is how many flies will there be after 5 days? So after 5 days just means that your x is 5. So we're just going to find f of 5. All right, so I might even use the value that's in the calculator still. And oh, maybe I should put the 5 in, sorry. So instead of 0.549, if it's still in my calculator, I'm probably just going to use that to punch in. So I'll take 100/3 times e raised to the, I'll put 5x in that case, because we have that x stored in the calculator. Because remember, this 0.549 was that value that we had stored. And again, what I end up getting is I end up getting about 519.615. Okay. And so in this case, it wants to know how many, like what is the population? So I'm trying to think of the best way to explain this. This does actually round, that we would say about 520 flies. And that makes sense because if it's decaying, then at that point, we haven't decayed to the 519th fly yet. So it would be about 520 flies after 5 days, okay? If you were showing work and you just put 0.549 in there, I think you end up getting about 518.8. So again, I would just show your work and I will understand what's going on. Because if you rounded in the model and that was an answer, if you used that correct answer going forward, I'm okay with that. But try not to round unless you have to. Okay. Now let's do some logarithmic problems. The Richter scale with earthquakes is one of the most popular things that I know of that uses logs. It says the magnitude of an earthquake of intensity I is given by R equals log of I over I sub 0, where I sub 0 equals 1. And that's the minimum intensity used for comparison. So in example 6, it wants us to find the magnitude R of an earthquake, given that I is 68,400,000. So that means we would just use this equation. R equals the log of, I have 68,400,000 in for I, and then over 1. And then basically you can just evaluate that. I mean, that's all they're asking you to do. So we would just take the log of, and then I can just use 68,400,000, and notice that I get about 7.84. And that would be our value on, that would be our magnitude on the Richter scale. Now, if they ask for the intensity of an earthquake, given that R is 7.63, well, then we would just put 7.63 in for R, and then we would have that times, equal to the log of, and then I'll just have I the intensity. If I sub 0 is 1, I mean, you don't need to write it, right? So we know that to solve this equation, what we could do is rewrite in exponential form, or raise both sides to the 10th power. So we have, or well, use 10 as a base, I should say. And so if we do that, or remember that when you see this common log, that's log base 10. So the base is 10, the log's exponent, or the answer to the log is 7.63, which means that's the exponent, and the argument is the value of the power. And so then what you could do is just take whatever 10 raised to the 7.63 is, and then we get this very large value. The intensity, like these are pretty big numbers, we can just round to the nearest whole number. So if we did that, that would be 42,657,952. So again, we'd say that our intensity is about 42,657,952. So that would be our intensity. Okay. The last thing is the chemical acidity of a solution is measured in units of pH. Here's another place where logs pop up. The pH is the opposite of the law of, the common log of the hydrogen ion. Okay, so the H plus is the hydrogen ion concentration in the solution. One little fun fact about the hydrogen ion concentration is this is often measured in moles per liter. Just so you know what kind of unit to put for those, okay? So this says if a sample of vinegar has a pH of 2.4, what is the hydrogen ion concentration? All right, well, let's just put 2.4 in for the pH, and that's going to be the opposite of the log of the hydrogen ion concentration. Obviously, we would then divide by a negative. And to solve a logarithmic equation, we can rewrite it in exponential form. So again, the base of the common log is 10. The exponent would be negative 2.4. And then that would give us the hydrogen ion concentration. Okay, so then again, we would just use our calculator and we would evaluate. We would just find what is 10 raised to the negative 2.4. And we get that it's about 0.00398. And so what you could say is that the hydrogen ion concentration is about 0.004. And again, we'll measure that in moles per liter. Or this is where, notice that our numbers can be very big or very small in these cases. And so you also, if you wanted to write it in scientific notation, you could say that it would be about 3.98, and then notice 1, 2, 3, so like times 10 to the negative third moles per liter. So I'm not sure the way that they sometimes express these different pieces, but just in case there's an answer in your text or whatever that's in scientific notation, just wanted a quick review of that. Okay, that is it. I hope you guys had were successful using the store key today, and that you were able to look at applications in these real life problems. Have a great one.